Hello, everyone. Good afternoon.
Mhm.
So before we start our meeting today, so this is the eighth meeting, and I hope you will be more early when joining the meeting. Especially, we are approaching the post half of the series, and this is where the international guest lectures schedules is. During after the post term of the lecture. So before our speaker today starts his talk, I would like to give a brief introduction. So today we are going to hear a lecture from Professor Dr. Akihiro Hazama. So Professor Hazama is a head professor in Fukushima Medical University, and currently he is also the vice president in Fukushima Medical University and in charge of international collaboration relationships. So Hazama Sensei earned his degree from Kyoto University and is a medical doctor, and he was also a visiting professor in Johns Hopkins University and also in Sensei, I forgot when you went to
UCLA,
Germany.
to
Yeah.
Germany
But
also.
probably
Yeah,
later.
yeah.
Yeah. You can give a more detailed
Yeah. Okay,
presentation.
okay.
Yeah. So Hazama Sensei is one of the board members of the Japanese Society of Physical Science, and is also a well-known author and collaborator with also the Nobel Prize winner Peter Egger when he worked on accompanying receptors. So Hazama Sensei, I would like to welcome you
Okay,
and
thank you.
thank you for your time
Mm.
for us today. And I
Okay,
understand that
okay.
you are 1 hour earlier than
Uh,
here
okay.
and 2 hours earlier than
Mm.
west of Indonesian side. So
Yeah,
you're
time
yeah, you're
difference is
currently
1 hour.
5 o'clock, I think, now in
Yeah,
Japan.
now 5:25. Oh,
Yes. Yeah.
yeah.
So Hazawa Sensei, the time is yours. You're
Okay,
welcome
thank
to
you very
start the lecture.
much.
Thank you very
Uh,
much.
okay, thank you, Dr. Ekar. So my name is Akihiro Hazama. So I'm working in Fukushima Medical University. So today's talk is what can be detected by electrophysiology. So I think that most of the students have not so much knowledge about electrophysiology. So I start with a basic. I start with my talk with a basic knowledge of electrophysiology. So before that, I just want to introduce my university. So this is Japan, and I'm living in Fukushima Prefecture here. So now Tokyo is here, okay? So about 200 kilometers north of Tokyo. So my university's location is here. This is Fukushima Medical University. So a couple of years ago, Dr. Eka was a graduate student in my university, and Dr. Eka got a doctor degree in my university. So Fukushima is very, very famous for the atomic power plant accident, so caused by the 2011 big earthquake and tsunami. So, and we just worry about the radiation problem by this accident. So, the, I remember that uh, Eka sensei was in Fukushima around this time, right? Maybe I remember that.
2013, Sensei.
Okay, 13. Okay, 2 years after the
After.
the earthquake. So okay. So and the location of Fukushima is here and Tokyo, and the, the power plant attacked by tsunami is here, okay? And so for the comparison, I just put the map of Chernobyl in Ukraine, now in the trouble of the war between Russia and Ukraine. But anyway, the uh, the Chernobyl location is here, and most polluted area is Belarus here, about 200 kilometer. So this is the same scale. So, and if uh, wind from north to south blowed at this time, maybe Tokyo got a big problem, but situation did not happen. Okay, just luck. Okay, so and now, but now still the now the government is working on the settling down the situation of a broken atomic power plant, but most area in Fukushima is safe and just we enjoyed daily life. So, okay, then let's move to today's topic. So, what is electrophysiology? Okay. So, electrophysiology is a method to study physiological functions by measuring electrical phenomena in living organisms. So this is just electrophysiology. So, well, in organ level, the electrical phenomena at the organ level. So maybe you know the such such examination, electroencephalogram, encephalogram or graph. Okay, so so we can measure the electrical function in happening in brain by using lot of electrode which attaches to the head. Okay, then the clinician can detect that problem of something like seizure or something like that by this equipment. So other thing, other example, so maybe you know this electrocardiogram, okay? So more, almost all around the world, in the hospital, we can get the electrical signal from the heart by this machine, okay? Then we know the problem happening in our heart by this method. Okay, so other example, I just put other example, electroretinogram. So this equipment can measure the electrical function happening in retina, in the eye. Okay, so by this equipment, we can examine the function of retina in our eyes. Okay, so such and there are other lot of equipment which can detect electrical phenomena at the organ level, but I just put 3 examples here. Okay. So today's topic, I will focus on the electrical phenomena at the cell level. Okay. So, so basically, I will explain two things. One is intracellular potential, and another one is ionic currents across the cell membrane. So, so this is something like a voltage, which we can measure by the microelectrode. And so this one, we can measure the current which passing through the cell membrane. So see, I will explain further from now. And I forget one thing. Another thing, it's possible to detect membrane capacitance, but this is topic is very, very complicated for the beginner. So today's topic, I will focus on two topics, okay? So first, intracellular potential measurement. So for the electrical phenomena of the animal, they maybe this guy is the first scientist who described the muscle function by the electrical stimulation. So this is a frog foot, okay, frog legs, and this is metal which hang the frog legs, okay, and this is another kind of metal, okay. Then he observed the contraction of the frog legs even after the frog died. Okay, so this is important. And see, Galvani was an Italian scientist, a physicist, and a physiologist, and he described this phenomena in a paper, in a book. Okay. So, one very famous scientist read this book, who is Volta. He is also Italian physicist. He's a professor of physics, and Volta is very famous for making battery. Okay, so he's the first person to develop the battery using two metal, zinc and copper, put in the H2SO4 solution. Okay, and then so Volta believed that the muscles were stimulated by the electromotive forces of the different metals. Okay, so he knows if he put two metal together, then ion movement happened. So he knows that. Then he thought that ion movement stimulate this muscle contraction. Okay. So it was around okay, the beginning of 19th century. Okay. So, and we moved to 20th century. Okay, so and one scientist described the potential generated by ion, ion concentration difference. So this is so two compartment solution. Okay, and this is here is a membrane which allow to pass the ions. Okay, the if so this so this two compartment just is a kind of a model of our body. Okay, here inside the cell and here is outside the cell, and if C is a concentration of some ion. Okay, and this electrical voltage described by this equation. So this equation is developed by Nernst. Okay, so we call this Nernst equation. So I just okay, I will write down just a moment. Okay, if something like potassium ion here inside the cell, for example, just example, if there is 100 millimolar potassium inside and 10 millimolar potassium outside, so this value is around I will just a moment. Okay. Okay. Around 60 millivolt. Okay. Okay. If there is 100 millimolar potassium inside cell and outside 10 millimolar concentration, then the voltage generated by potassium ion is minus 60 millivolt. The minus means outside 0 is inside is minus 60 millivolt. Okay. So, okay. So, but if we think about our body, there is several ions. Okay. So, most important ion is sorry, potassium, and other one is sodium. Okay, sodium ion, and other one is chloride here. Okay, just a moment, it's messy, so I just sorry, how to sorry, oops. So, and if three ions exist in the cell and outside solution, the membrane potential, intracellular potential is described by this equation. This equation is called Goldman equation. Okay, so PNA, PK, PCl is a permeability ratio of each ions. Okay, so normally sorry, just a moment. Normally, P potassium, P sodium, P chloride, P chloride. So normally, in our cells, potassium permeability is greater than sodium permeability or chloride permeability. So in that situation, membrane potential, intracellular potential is mainly generated by potassium ratio between inside and outside. So that means if we change the outside potassium concentration, then our membrane potential, intracellular potential of our each cell can be changed by that. Okay, so this is just the example of the membrane potential of the I think the muscle cell, and just increase the outside potassium concentration, then membrane potential is getting close to 0 millivolt. So okay, so this is very important because in clinic sometimes we use potassium ion for the treatment of patient, but by mistake, if we put too much potassium in the patient blood, then heartbeat stop. Okay, then so maybe you can examine the terrible thing happen by that. Okay, so fat intracellular potential measurements can tell us so activity of nerve, muscle, and endocrine cells, etc. Okay, and also we can detect the electrical response to extracellular stimuli like a hormone response. Okay, so and intracellular potential can be measured by microelectrode. So we can make a very sharp microelectrode by glass capillary. So then using microscope, we can check the cell, and just we can impale the cell by the microelectrode. Okay, then we can measure the voltage of the cell. So sometimes we just call membrane potential instead of intracellular potential. So those are just same word. Okay. So this is a commonly used battery, and this is 1.5 volt. Okay, and but in our cells, voltage up to 20 millivolt and down to minus 90 millivolt, so around that range. So this is my old picture. I'm here. I started my career by studying the hormonal response of HeRa cells with microelectrodes. I was in Kyoto University at that time. My lab is such old building which built 100 years ago. So everything is just old, and I started from here. Okay. So HeRa cell, I will explain. So HeRa cell is an immortal cell line And so it is the oldest and the most commonly used human cell line. This cell line is from the cervical cancer uh, taken from the Henrietta Lacks, the African American, and she was the mother of 5 children and who died of cancer on October 4th, 1951. And the Johns, he died in the hospital of Johns Hopkins University. And at that time, the doctor just put his cancer cell in the glass dish. Then the cancer cells start to grow. Okay, and now her cells, many laboratory in the world using her cells for experiment. Okay, so even we can get this HeLa cell by the cell bank, so commercially available. Okay, so I just use microelectrode and I just measure the membrane potential change by the hormonal response. So then I found histamine. Histamine can induce the membrane potential change. So this is a membrane potential measured by the microelectrode. This line is 0 millivolt, and upward, this is a minus 80 millivolt. Okay. So and so the next cell, by I apply histamine, then get the signal here, and again histamine, and another signal, and I apply several times, and finally, maybe cell got tired by the application of too much amount of histamine. Well, anyway, then first time we described the HeLa cell has a histamine receptor, okay, by this experiment. So on the other hand, I apply a different kind of hormones, secreting serotonin or VIP, but no response. So only histamine has a good response. Okay. So this is the first discovery for HeLa cell has a histamine receptor. It was this paper was published 1985. Then we moved to another experiment. I use intestinal cell line, intestine 407 cells. By looking, it's very similar with HeLa cell, but anyway, we found one thing. If I apply hypotonic solution outside the cell, of course cell swells, but at the same time, cell shows the membrane potential response. Okay, so this is a resting condition, and by hypotonic solution, we can get such type of response. Here, the downward is a minus millivolt. Okay, so such response we reported in 1988, long time ago. So for this experiment, we measure the intracellular potential changes. So this is important. So this membrane potential change means a change in membrane ion permeability. So, and two possibilities we can expect. One is increased ion permeability. So, and another one is decreased ion permeability. In both cases, membrane potential change happen. So we should think about two possibilities. Okay. So how to examine the membrane ion permeability? How to examine? One way is it is very important. So replacement of ions, like replace sodium by potassium, or replace chloride by other anion, okay, something like that. And another way is we already know that there are many types of ion channel blockers. So, and so we can, use ion channel blocker to show the what kind of ion channel is involved in the membrane potential change. So, so this is a membrane potential change by a hypotonic solution. So we detect such type of membrane potential change. So then I apply potassium channel blocker, which name is quinine. Then such change diminished by this potassium channel blocker. So this means this membrane potential change is caused by the potassium channel opening. Okay, so then if I use blocker, then this change, this response diminished. Okay, next we apply chloride channel blocker named SITS. Okay, then I found interesting response, something like that. So this phase diminished. Okay, so this is very interesting, just like that. Okay, so maybe this phase chloride channel is involved in this response here. Okay, so then ion replacement. So this one, chloride concentration is around 60 millimolar, but we decrease chloride condition by other anion, then we can change the response shape, okay, like that. And I did another experiment. I use calcium-free solution, calcium-free, then this response diminished. And this is interesting. Low chloride, almost chloride-free, and calcium-free, then response is like that. So, and maybe then I thought that this hyperpolarization, the if membrane potential goes down, we call that hyperpolarization. So this hyperpolarization is calcium dependent, but this phase chloride dependent, but calcium free cannot diminish this signal. Okay. So then I will explain the role of those ion channels. So I will explain cell volume regulation under hypo or hyperosmotic conditions. Okay, this is a normal cells, isotonic condition. And if I apply hypotonic solution, then maybe you can imagine cell swell, water move in the cell. Then the cell shows a swelling. But during a couple of minutes, cell goes to original volume. This process called regulatory volume decrease, RVD. Okay. On the other hand, we apply related with the this RVD process. Okay. So then I measure the cell volume. Okay. So I used the cell volume counter, which is used in hospital, which measures the red blood cell volume and something like that. Okay, we got old equipment and I used for my experiment. And then this is a cell volume change. So by hypotonic condition, cell swells, but gradually return back to the normal volume, okay, in 2 or 3 minutes, okay? And a high potassium condition or potassium channel blocker blocks the cell recovery, cell volume recovery, okay? So, and other thing, chloride channel blocker also block the cell volume recovery. And in case of low chloride condition, cell volume recovery increased. Okay, enhancement of RVD by low chloride. Okay, and in the calcium-free condition, something like that, cell volume recovery can be could be blocked. Okay, so and another thing I did is we can measure the intracellular ion condition using special microelectrode, ion sensitive microelectrode method. So this is a glass capillary electrode, and we put ion exchanger resin, okay, which are permeable to potassium or calcium or chloride. There are several types of exchanger, and by using such method, we can measure the intracellular ion condition. So by using such electrode, we measure the intracellular calcium concentration by calcium selective electrode. So by hypotonic stimulation, this is a membrane potential change. And this is a calcium change. So calcium increase by the hypotonic condition, okay? So finally, we made a model of, uh, uh, of this phenomena. By hypotonic stress, water move in the cell, and cell shows swelling. Okay, by swelling, chloride channel can be triggered. So this chloride channel open. So we put the name of this chloride channel, volume sensitive chloride channel. So this is the first finding which detect such a type of chloride channel. Okay, and another thing, so we measure the calcium increase, and then this calcium can activate one type of potassium channel. So this is calcium activated potassium channel. This channel was already reported in different type of cells, but in our cell, this potassium channel can be activated by calcium. So these two channels collaborate together, then ion movement happen. See, potassium outflux and chloride outflux. Then water is was derived from inside to outside. Then the cell return back to the original volume. So this process is the basic mechanism of RVD. So we established this idea, okay, by different type of experiment. So this is one example of the membrane potential measurement is very strong tool for detecting such phenomena. So, this is a lecture for the students. So it is not my experiment, but I just introduced the measurement ionic currents across the cell membrane. So here I introduced two big scientists. One is Huxley and one is Hodgkin, Huxley. Okay, so they made a model of the cell membrane by electrical parameters, or capacitor, resistor, and battery, such so such thing is called equivalent circuit. Okay, so and they assume that there is some pathway for the ions, and for each ions there is a specific pathway. So there I think their idea was very, very nice, and he just built the concept of ion channel. So actually, they used such type of animal, squid. Okay, squid. There is a big giant axon here, giant nerve. Okay, so and by just like using binocular, he can they could isolate the giant axon using scissors and forceps and such equipment. So, and they measure the function of the nerve. Okay. See, actually, so this is a nerve, and they put voltmeter here. Then he can measure, they could measure the membrane potential of the axon. Okay, so and so they developed special type of equipment method called voltage clamp. So they fix the membrane voltage by using amplifier. Here they fix the membrane voltage minus 80 millivolt by the electrical equipment. Okay. Then they measure the current flow. Okay. So this idea is very, very great. Okay. And by such type of equipment, they could detect the current flow, ionic current flow, which happen in axon cell membrane. So this is an example of the experiment. So first, they fix the membrane voltage at minus 60 millivolt. Then rapidly, they just change the membrane potential down to 0 millivolt by using their apparatus. So then they observed such type of membrane ionic current like that. So and he found that this ionic current has two components. One is potassium, one is sodium. Okay, so this is action potential which happen in giant axon. And first sodium sodium permeability increase. Then potassium permeability increase. So sodium permeability increase, then sodium, okay, I will write down, just a moment. So this is a cell membrane. So by, first sodium enter in the cell. So, and after that, potassium move from inside to outside. Okay, so this is a mixture of sodium current and potassium current. Okay, so they succeeded to describe the ionic current for each ions. So they are very, very great. So then finally they made a Hodgkin-Huxley model of the cell membrane, and the potassium current and sodium current. This is the potassium channel and sodium channel, and other they just say leakage current, and maybe this is chloride, and so such models they made. Okay. So then I will move to next topic. Hodgkin-Huxley was a British scientist, and Erwin Neyer and Bart Zachman are German. Okay, so they developed the method which called patch clamp. Okay, it's an advanced method of voltage clamp. Actually, they got Nobel Prize in 1991. So what is patch clamp? See, they use special electrode, not impale this cell membrane, but just attach the cell membrane and put the negative pressure here. A membrane was sucked in the electrode. Then here we can, they could measure the very tiny current which move through this membrane. Okay, so the membrane current is like that. It's very interesting, just like on and off of the current. So then they notice that the ion channel has an open state and closed state. And so then this current happen, they observed. So this is the first demonstration of the single channel ion channel. So, and so this is an idea of ion channel, open and closed state, and here is a gate. And another example, so gate is here in closed state. This part is just moved to the here, then the channel close. There are two type of ion channel. Okay. This is equipment of my lab, and this is electrode, and using electrode, we can get such ion channel signal. So time is limited. So I'm not getting to detailed method, but just simply I explain something of the patch clamp method. Okay, so so this is a patch pipette, patch electrode, and attached here. And another way of measurement is just break this membrane by using some drug. Then we can measure the whole membrane current which across the whole cell membrane, or by sucking this membrane. Then okay, same thing, just those two are same. Okay, we can measure the whole membrane current. So this experiment is called whole cell method, or whole cell configuration. Okay. Sorry in Japanese, but anyway, so this is a single channel recording. So we can, in this condition, we can just measure the current which across this ion channel, okay, like that. Okay. So this is another example of single channel current measurement. And okay, by stimulus, maybe 100 millisecond or so, and we can apply many times this stimulus. Then we can get the single channel opening here. So by each stimulus, we can get the single channel opening, and we can make summation. We can get such type of potential change. Okay, so we can do such type of experiment. So, okay, just I will skip. We can, many people working on using this technique and measure, they measure a lot of cells. So this is my experiment, and I did a special experiment which detect ATP release from the cell. And so this is a patch pipette, and this is some cells which has ATP receptor, P2X type receptor. Then we can get the signal from the cell. So I did this experiment to know that the local amount of ATP near the cell membrane. So by using such method, we can detect the concentration of local area near the cell membrane. Okay, so we call this biosensor. Okay, so then okay, we still have time, and I will explain ligand and ion channeling interaction. So here, this channel is one example of ligand-gated ion channel. Okay, so if so, this channel has a receptor for some messenger or ligand. Okay, so ligand bind to receptor, then channel open, then ion can move through this ion channel. Okay, so there are many types of receptor: acetylcholine receptor, GABA receptor, glycine receptor, AT receptor, P2Z, and I should mention one thing: P2X, P2II, P2X type. Okay. And next, I will explain ion channels regulated by intracellular messengers. Okay. So I will introduce one type of ion channel which is stimulated by cyclic MP release. So today I will explain CFTR chloride channel. Okay. The another thing, calcium can activate it, potassium channel, or some type of chloride channel. So, and there are calcium activated potassium channel or calcium activated chloride channel also. So actually, I show this picture before, and here, this potassium channel can be activated by calcium. So calcium is a messenger for this cell, and calcium can activate this type of potassium channel. And HeRa cell also have this. So in case of HeRa cell, the histamine binds to histamine receptor, then calcium increase inside the cell, inside the HeRa cell, then that calcium can activate this type of channel. Then we can get the change of the membrane potential by histamine stimulation. Okay. So from now, I will explain one type of chloride channel, which is highly related with this disease, cystic fibrosis. So we just use CF instead of cystic fibrosis often. And this disease is a genetic disorder that affects most of the lung, but also the pancreas, liver, kidney, and intestine. Okay, and so long-time issues include difficulty of breathing and coughing, and mucus accumulation in the lung. Then chronic lung infection happen. So before World War II, this is a genetic disease, and this patient mostly died before 10-year-old. But after the World War II, there are antibiotics, many types of antibiotic drugs was available. Then the patient life is become much longer, but still a big problem. So this disease is not so much in Asians, so Japanese and Indonesian also, and among Caucasians, white people. So there is one CF carrier for every 25 people. So this means many carriers, okay? And one CF patient for every 2,000 people. So many patients exist in Caucasians. So this is a very problem for Caucasians. Okay. And so carrier partner married and got a baby, and by chance they got CF baby. Okay. So this is a lung of CF patient, and mucus accumulate in the alveolar of the lung, and this is a very good condition for bacteria to grow. So this disease causes dysfunction of the lung. Okay, why this happens? So by many research, so we know that the reason of the water secretion is got damaged by this disease. So mechanism of airway water secretion absorption. So there is a airway gland, and sodium chloride and water moved from this, and mucin, this mucus moved from here to outside. Then mucin is here, and some water is just absorbed from the epithelial cells, and by this water secretion, mucins got softened by the water. Then mucin get easy to move from the deep inside the body to the outside the body. Okay, so there is a cilia movement here, and this mucin is just forced to move towards the mouth. Okay, but in CF patient, this water movement is not enough. So the mucin accumulate here. Then lung got this condition. So this is a sweat gland, okay? And so As in case of sweat gland, sodium chloride and water move from inside the body to outside. Uh, then the so this sweat movement, sodium chloride just absorbed uh, from by the duct. Then sweat is actually hypotonic, more hypotonic than the blood. Okay, so what happened in CF patient? So normal people see this duct cell, sweat duct cell, and chloride and sodium move, and this sodium chloride movement just make us hypotonic sweat. Okay, but in case of CF patient, by many research, chloride movement was got disorder. So there is a disorder of chloride movement. Then sodium chloride cannot move from this lumen to blood side. Then sodium chloride remains in the sweat. So there is an old saying: if your baby tastes of salt, he is not long for this world. So this is an old saying. So, but old people notice that if the mother get baby and mother just taste the maybe the some cheek or something like that, then he is salty, and in that case it's a pity that he is not long for this world. Maybe this is a CF patient. Okay, so in case of CF cystic fibrosis patient, that sweat is not hypotonic but more sodium chloride concentration. So this is a idea of cystic fibrosis research. Okay, 1983, the Paul Quinton just discovers a dysfunction of epithelial chloride transport in CF. He published in Nature, and 3 years later, two scientists, Frizzell and Welsh, just published a paper in Science or Nature, mentions that the dysfunction of ORCC, this is an outwardly rectifying chloride channel in CF patient. Okay, so this channel function got damaged. Okay, in 89, a Canadian group published one paper in Science. He just found the gene which related with this disease. So he put the name to the gene CFTR. So I explain later. And in 1990, so this one, in the investigation of substances blocking CF channel. So actually, this project is not successful, but actually I joined this project. Okay, so but later, so CFTR is a cyclic AMP activated chloride channel. So two scientists found and published in Science and Cell. Okay, and but interesting interesting thing is this CFTR ion current is so much difference in ORCC. But later, we know that CFTR regulate other chloride channel. This is published in Nature. And also CFTR regulate this channel by ATP release. This experiment was published in Cell. So this is a basic idea of the history of cystic fibrosis. So my research in Germany, it was 1998 and to 1991. I was in Frankfurt am Main. it was historical time. When I entered in Frankfurt, it was West Germany. But during this time, okay, so East Germany just got mess, collapse, Soviet Union also. Then there is a one big Germany when I was in Germany. So I work in Johann Wolfgang Goethe University, Frankfurt am Main. So Frankfurt is a very big city, and it's a center of money. Okay, so money is just moved to this city, and there's a big buildings, bank building, many bank building. Okay, so many rich people, but not me. Okay, so I worked in the university around here. So this is a river here. So my university is around here. Okay. So I worked in Centrum der Physiologie, Center of Physiology. So my boss was Professor Fremter. See, he was an outstanding scientist in the field of renal and epithelial physiology. So he established concept of tight epithelia and leaky epithelia. Okay. So he established many important methods in electrophysiology. So he is okay. I think he's one type of genius. So he just think about. He noticed a lot of things, and he has many ideas. So when I joined his lab, he asked me a lot of things. Okay. Do that. Okay, then I told him it's not possible, and he often told me what is theoretically possible can always be accomplished. So he always tell me like that. So this is a terrible time for me. So he is genius, but it's not me, and he asked me a lot of things, and it's very messy time for me. But I learned a lot of things from his lab. But anyway, it was hard time for me. Okay. So when I just moved to Germany, one big paper appeared from the Canadian group. Both was Riordan and a Chinese Canadian scientist, Dr. Tsui, and he reported one protein, membrane protein, is related with cystic fibrosis. So he just put the name of the protein, cystic fibrosis transmembrane conductance regulator, CFTR. So the structure is like that. Okay. Sorry in some part in Japanese, but anyway. So ATP binding domain here and here. Okay. So structure is like a pump of some ion or some something. Okay. So expected role of CFTR. Very simple idea was this CFTR itself is a chloride channel. And another idea is CFTR is something like a subunit of the ion channel. So this is next idea. And one complicated idea is that CFTR can pass some material, some component, and this one block the chloride movement. So this is German hypothesis. So they were working with this hypothesis, but this is the correct answer. Okay, so what I did in German lab. So this is a patch clamp electrode. So this is a cell membrane of the airway cell, and this is a chloride channel. So actually, we can excise. So this condition, this configuration called excised patch experiment. So actually, we can excise this cell membrane from the whole cell. So this just some patch of membrane here, okay? So by lifting up this electrode to the cell, we get this configuration. Then interesting thing is, so we can observe the ion channel activity by this configuration, okay? So by time, 10 minutes later, after the making this configuration, so most of the chloride channel open here, open time just increase. So what we did next, we apply cell extract material here. Then what happened? We apply cytoplasm here. Then channel close. Then wash out this one. Then channel activity reappear. Okay. So this means some materials in the cytoplasm can block this ion channel. So this is ORCC, okay? So cell extract substance blocks chloride channel. This is our observation. And we were focused on the detecting this substance, but not successful because there is a one big paper appear in other lab, and so that is CFTR itself is a chloride channel. It is different from the ORCC chloride channel. Okay. So this is not my experiment, but experiment from other lab, American lab, and this is ORCC current here. So by application of pK, which pK is a cyclic AMP dependent protein kinase, and then such type of some change we can observe this part. So this small current is carried by CFTR, okay? So pKa activated here. And they applied antibody which bind to this one, then this current diminish. So the antibody just broke this current, then return back to this condition, okay? And there is a drug which broke ORCC, then completely diminish, channel activity diminish. This is a good example which shows there is two type of ion channel in this cell membrane, and it's independently working. So, and so now we knew that CFTR is a chloride channel itself, not different. It's different from ORCC. So what happened for me? What happened for me? So one day, Dr. Fremter calls a lab member to his office, and he mentioned as, I want to stop this project because it's a loose game. so we want to claim the situation because maybe our idea, our project have maybe something related with disease, but he always want to win. Okay, so win is very important for him. So okay, then I decide his love is not good. So I decide to move from Germany to Japan. Okay, so I send a letter to my boss to Japan, in Japan. At that time, there is no email. So, okay, so I just write a real letter. So 1 month later, I get answer from my boss. So your position is not available in Japan, or please stay in Germany. So I got very, very disappointed. But I started write letter to other universities, and I just make a letter saying, so your experiment is very, very nice and excellent. So I want to join your lab. Then I just put a different professor name and different address, and maybe I just put 30, nearly 30 letter to different universities, and finally I got the answer from UCLA, and I moved to UCLA. But this is a role of chloride channel, which involved in cystic fibrosis. So this is a cyclic MP dependent chloride channel, okay, and regulate other ATP release, and an ATP can regulate the other type of chloride channel over CC. And I skip this topic, but also there is other sodium channel, epithelial type sodium channel, and this is also regulated by CFTR. So this is I just explained this lecture, CFTR, for the example of second messenger activated ion channel. Okay. So my talk is just finished right now, and I just want to say that for many scientists, electrophysiology is an unfamiliar method. So because maybe people got the idea of very difficult and messy and such things, but if one has a knowledge of electronics, one can assemble the device inexpensively in cheap price. Because when I started my experiment around 1985, we don't have much money, so I often make the amplifier by myself, and I did we did experiment in cheap way. So but important thing is knowledge of electric device. So it's all for all my talk, and Dr. Eka asked me to ask me to make a email address. Sorry, my pen has oh, just like so. Sorry, I just changed the way. Oops. I write down. Okay. So if you guys have questions, please send me email. Not a real mail, but now life is very become very easy, and so just send me email hazama@fmu.ac.jp. Okay, so maybe still have some time, so I can ask, I can accept some question. Okay. Okay, Eka. So my
Okay,
talk is over.
thank
So
you. Thank you very much, Hazama Sensei.
yes.
So, I hope everyone understands the what Hazama Sensei explained it. So it's very important if you want to study or explore potential drug lists for pharmaceutical products, you have to know how the receptor and the drug interaction works.
Mm,
So Hazama Sensei is an expert in cellular physiology. So you are welcome to ask more related to the lecture, or probably not so related to the lecture,
mm.
and you can ask also in Indonesian, and I will try to translate to Hazama Sensei
Okay,
for
thank you.
you. Jadi yang mau bertanya saya persilahkan, bisa juga dalam bahasa Indonesia. Jadi materi kenapa kami mempertimbangkan memasukkan materi Hazama Sensei, karena sebelumnya teman-teman sudah mempelajari eh, mungkin interaksi suatu potensi obat dengan reseptor melalui, bisa memprediksi melalui ini ya, molekular docking. Tapi kalau untuk lab basahnya itu elektrofisiologi, dan tadi ada metode patch clamp, itu salah satu teknik yang sangat kuat untuk mengkonfirmasi apakah memang benar suatu channel itu terbuka, apa tertutup, atau binding terhadap suatu ligan. Jadi untuk ahli PHK juga tidak banyak ya di Indonesia, bahkan di dunia. Hazama Sensei itu salah satunya. Tadi bisa kalian lihat tadi juga kolaborasi penelitian sama orang-orang yang memang sudah peraih Nobel. Jadi monggo kalau misalnya ada yang mau bertanya, eh, bisa juga dalam bahasa Indonesia ya. Tadi kayaknya ada yang raise hand. Muhammad Wisam, silakan.
Okay, thank you for the time.
Yes.
Good afternoon, Mr. Professor Akihiro Hazama.
Mm,
My name is Muhammad Wisam from Brawijaya University. I have some question, especially from cystic fibrosis.
mm.
The question is the cystic fibrosis in lung. They have one of the cause. They have a same morphology in acute respiratory distress syndrome disease, especially in COVID-19. This is my question, and thank you.
So, okay, see, COVID-19. So people got often the lung infection, and it's cause this dysfunction of the lung. Then, especially in the early 2020, at the beginning of the worldwide spreading of COVID-19, many people got severe damage of the lung, and maybe CFTR is related that the pathological condition. So maybe if we can, so in that case, this water movement, okay, sorry, just a moment. Water movement makes the situation much worse. So too much water is exit inside the lumen alveolar, then air oxygen movement is got damaged. So in that case, maybe by suppressing of CFTR is a good way of treatment. This is one possibility, but there is not so much challenge for that way. So, but my idea is it's worthwhile to examine the some drug which affect CFTR, which can cure the COVID-19 lung problem. So it's suitable answer for your question.
So, Muhammad Wisam, do you want to respond to Hazama Sensei?
Yes, but something I don't understand.
So, okay. So in case of, just a moment, just a moment. So in case of lung infection, oops, sorry, just a moment. So, and so maybe in case of COVID, such water movement occur. If too much water is in here, then also the oxygen movement is got diminished. Okay, so to block this too much water movement, to block this too much water movement, one possibility is if there is a CFTR blocker, it's worthwhile to apply CFTR chloride channel blocker here. Then this water movement decrease. Then maybe the oxygen movement got increase. This is my idea. So I'm not sure this is right answer, but for the COVID-19 treatment, I think it's worthwhile to examine the ion channel blocker to cure the COVID-19. So this is my idea. Okay.
Okay. Thank you very much, Sensei. I think we have also lots of people raising their hands.
Okay.
Probably,
Thank you.
Wanda, you are welcome to address your question.
Okay, thank you for the opportunity, Dr. Eka, and thank you for the presentation, Hazama Sensei.
Mm.
Sorry, I asked in Indonesian.
Okay.
Bagaimana pendapat dari Hazama Sensei mengenai transplantasi organ yang gagal atau dalam artian tubuh menolak organ tersebut? Apakah terkait dengan kelistrikan yang ada dalam tubuh? Dan bagaimana mekanisme dari penolakan tersebut? Thank you very much.
Okay. So, Azama Sensei, the question is
Yes.
during possible organ transplantation, there are sometimes rejection from the host. And does that have to do with the electric current, probably in the host body? Probably the unstable ion current, probably in some cellulose or tissues, probably.
So the question is, in case of organ transplantation, the electrical stimuli can help the transplantation. So I'm not sure, but okay. For example, just a moment. I will change the slide. Oops. It's better to have white paper. Just a moment. Oops. Brain, spinal cord. So then sometimes we got the damage in spinal cord here by some traffic accident. So it's not easy to cure this condition before, because if got damage here, then fibroblast start to grow, and this blocks the nerve repair. But sometimes now we know that some electrical stimuli here or here, then this helps the nerve growth. Oops. So this stimulation induce a nerve growth. Maybe such things, such technique can used for different type of organ transplantation. So I'm not sure each method, but sometimes electric stimulation is useful to enhance the nerve growth. So I think it's a good way to think about that. Okay.
Jadi Wanda, mungkin dari penjelasannya Hazama Sensei yang terutama yang di current level yang di ini ya back spine yang spinal belakang itu yang paling utama. Jadi selama yang bagian sininya tidak ini damage terutama karena trauma yang mungkin akibat kecelakaan apa itu kemungkinan sih nggak terlalu ini ya. Kalau respon ini donor organ sebenarnya bukan lebih ke electric current ya, tapi penolakan sistem imunnya sendiri. Jadi kalau misalnya ada benda asing yang tiba-tiba diintroduce ya defensive mekanismenya pasti menolak itu. Tapi kalau yang elektriknya selama yang di bagian utamanya itu udah terdamage sih nggak masalah. Mungkin begitu deh. Oke, next is Siti Zainia. Siti Zainia, oke.
Yeah. Is my voice clear?
Okay, do you want to go first? I'm not sure. Siti Zainia and Fitriani and Nirwana. You are welcome to address your questions.
Okay.
Okay. Is my voice clear?
Yeah.
Yeah.
Thank you, Dr. Eka, for the change to give me the time for giving my question. Thank you, Prof. Hazama, for the great explanation. I'm Siti Zania from University of Mataram. My question is about RPD mechanisms. I would like to ask about does RPD mechanism has the same process in all the type of cells? That is my question. Thank you, Prof.
So it's sorry, it's a little bit difficult to listen. Eka, can you ask? Okay, can you hear the question? Sorry.
You can repeat the question.
Okay. I would like to ask you about the RPD mechanisms. My question is, does RPD mechanism has the same process in all the type of the cells?
Okay. So basic. Okay. So today I explain the ion channel, CFTR, and I explain calcium activated potassium channel. So, and I explain volume sensitive. Okay, CFTR. So, fat organ have CFTR. Airway cell and pancreas and intestine and something in heart muscle cell, but not brain. So not all the organ have CFTR. Okay, and for calcium activated potassium channel, many type of cell has this type of channel. So maybe this. So ubiquitously, this channel exists in our body. And today I also explain the volume sensitive chloride channel. Cell volume increase, then chloride channel open. this channel is mostly existing epithelia, and cardiac muscle. So if cell volume change happen, then in case of such organ, this channel is very important. Okay, so many organ has their specific ion channels, and so then some mechanism changes during each organs. But important thing is we should know the basic knowledge about the ion channel, ion movement. Then we can apply to the lot of phenomena. So first learn the basic idea, then apply to the many organ. So it's okay?
Yes, thank you.
Okay, thank you. Next question. Yeah, probably just two more. Who wants to go first, Fitriani or Nirwana? Please address your question.
Okay, okay, thank you. Thank you to Dr. Eka.
Okay.
Thank you for the explanation, Professor Hazama. My name is Fitriani from Mataram University. Permission to ask question. Previously, it was explained about the hormonal response of HeLa cells. If the hormonal response of other cells the same or different? If different, why does this happen? Thank you, Professor.
Okay. So this is an example of the HeLa cell response. So each cell has a different type of receptor. So this is a cell, and this is something like a receptor. And HeLa cell, H1 type histamine receptor. So if the cell has one cell has H1 type histamine receptor, then maybe we got similar result. This H1 type receptor, if histamine is just attached here, then what happens next is calcium increase, inside the calcium increase. Okay, so but many other cell has not H1 type histamine receptor, then we do not have this membrane potential change. So in other words, by using this method, we can examine very easily a lot of hormones. We can apply a lot of hormones. Then we know that this cell has this type of receptor. So it's very easy to do that. Okay. So using similar experiment, many people demonstrate many type of hormonal receptor by this method. So this is a very cheap way, but very effective method to detect hormone receptor. Okay.
Okay, thank you for the
Okay.
explanation, Professor Azama. One more question, it's okay?
Okay.
Okay, what happens if the cell permeability increases or decreases? What effect does it have on cell response?
Okay. Here. So if some ion permeability increase, then membrane potential change, and also decrease of the ion permeability. This also the change the membrane potential. The one, so this is a here potassium permeability increase. Potassium permeability increase by histamine. Okay, this is an example of the increase of the potassium permeability. So I show another example. Sorry, just a moment. I write down. Pancreatic beta cell. So this is an endocrine cell which release insulin. Insulin. Okay, so and this controls sugar. Okay, maybe you know that blood glucose is regulated by insulin. So in this case, so glucose by eating food, blood glucose increase and glucose enter into the cell. Okay, maybe you can understand. Okay, by eating food, glucose increase. So what happened next? Then ATP synthesis increase. Okay, maybe you can understand. Okay, so what ATP did next? There is a potassium channel called KATP. Okay, so KATP is interesting. So ATP, if ATP increase, then this channel close. Okay, so this channel close. This means in case of ATP increase, potassium permeability decrease. So what happens next? Membrane depolarization. So just a moment. Oops. Millivolt. Cell membrane of beta cell minus 80 0. So by glucose. So membrane potential become less negative, go to positive by blocking this channel, and PK decrease. Then this happened. So what happened next? There is a voltage-dependent calcium channel. So this membrane potential change just open the calcium channel. Then calcium increase. So calcium enhance the insulin vesicle. So this is a vesicle which contain insulin. So and exocytosis happen. Okay. So in this cell, so permeability decrease is very key phenomena in the insulin secretion. Okay, so this is one example. So there are a lot of type of example, but anyway, please remember this type of phenomena. Okay.
Okay, thank you.
Thank you very much, Sama Sensei, for the. This is a very new information, I think, for all the students.
Okay. It's
So,
worthwhile to check.
probably, yeah, I hope we have more time, Hazama Sensei, but I'm afraid we only have one more question left.
Okay.
So, yeah. So, Nirvana, you're welcome to address your questions.
Okay, thank you so much, Dr. Eka, and thank you so much, Prof. Hazama. My name is Nirwana Hakiki. I'm from University of Mataram. Actually, I don't really recognize about the Goldman equation, but from the article I read, Goldman equation explain the uneven distribution of iron across the cell membrane. My question is why this happen? Maybe there are some factor, internal or external, affect it. That's all. Thank you.
So maybe your question about the Goldman equation. Okay. So see, first I should mention that so this is very simplified equation because so there is a cell. Of course, potassium here, sodium is very small, chloride some, but there are other type of ions like calcium, magnesium. So especially calcium is sometimes very important to change the membrane voltage, membrane potential. So we should, it's better to put calcium ion here to this equation, but to put calcium in this equation, the equation become very complicated, very complicated. So in a textbook in physiology or biology, maybe most of the textbook just explain Goldman equation, but not the calcium involvement. But actually, calcium also very important to change the membrane potential. So we should remember that this Goldman equation is very simplified equation. So I'm not sure this is a right answer for your question, but.
Is it okay, Nirvana?
Okay, and I just want to one other thing. Go here, in, out, but only chloride. Chloride is here is out and upper one is in. But why does this happen? Because this is negative charge. Negative charge. Then in and out is just change. Okay. So sodium and potassium is positive charge ion. So in and out here, but chloride is negatively charged. So out and in.
Okay.
Okay.
Thank you very much, Hazama Sensei.
Okay.
So I think your explanation is very new information for all the students, and it's very important to understand. And I
Okay.
hope there is a chance for us to invite you again, specifically to learn on the basics. And then,
Okay. So
yeah,
basic knowledge is very, I think, very
yeah, basic
important.
knowledge is very
Then
important. So, but anyway, today's lecture is very insightful, Sensei, and it's very important for
Okay, thank you.
the development of our young scientists today, and hopefully most will be more interested in working in this resource area in the future. So I'll probably I will give the floor to the operator, or I mean, do you want to present something to Hazama Sensei? You're welcome.
Thank you very much for the lecture, Professor Akahiro Hazama. For showing our appreciation, we would like to share screen the certificate.
Okay, thank you very much.
Thank you very much, Professor Hazama.
Thank you.
Thank you very much, Hazama Sensei.
Thank you very much.
Let's give a round of applause to
it's good.
to Hazama
It's good. Really nice.
Sensei. So can all of the students probably turn on the camera for we can
Yeah, right.
get
It's a
nice
good
photo shoot.
idea. It's a good idea.
I think some of the participants already like, but it's okay. Ya, silakan diarahkan operator dan langsung ditutup ya. Mungkin nanti post-testnya menyusul seperti biasa.
So it's time to smile, okay?
Okay, let me take a picture.
Okay.
1, 2, 3, cheese. Okay, next slide, please. 1, 2, 3. Okay, thank you very much for the participation on this lecture.
Okay.
All of the participants can leave this Zoom meeting. Untuk post-testnya nanti akan dikirim melalui grup MBKM. Terima kasih.
Thank you,
Sensei,
Prof.
thank you
Terima kasih.
very much.
Terima kasih.
Terima kasih, Prof.
Terima kasih, Prof.